Hey everyone, welcome back. Today we're going on a really fascinating data journey in C. We're actually going to scale what I like to call a complexity ladder together. We'll start off with everyday linear ways to store information, and then step by step we'll figure out how to navigate highly complex, interconnected networks. So let's dive in and see exactly how data transforms from a simple list into a sprawling city grid. Here's our roadmap for today's explainer. First up, we'll look at dynamic structs and arrays. Second, we'll tackle binary search tree operations. Third, we're navigating city graphs. And finally, we'll wrap up with a showdown, BFS versus DFS. All right, part one, dynamic structs and arrays. Let's start at the bottom of the ladder with linear data. Picture a basic calendar app. It's not just a single number, it's a whole collection of details, right? Well, in C, we group all those related details together using a struct. Our struct day acts as this perfect little container for real-world schedule data. And because it uses dynamically allocated strings for the day's name and the activity, we only ask the system for the exact amount of memory we need at runtime. No more, no less. It's our foundational building block, giving us a really clean, efficient, linear array of information. But hey, a single day doesn't make a whole week. To actually build out our calendar program, we need a life cycle, which we break down into 3 logical steps. First, our create function dynamically allocates memory for exactly 7 days. Second, the read function jumps in to capture the user input, things like day names, dates, and descriptions. And finally, the display function processes all that raw data into a weekly report. Notice how separating these tasks follows that core design principle of separation of concerns? It keeps our C code modular and, frankly, way easier to debug. So how does that final step actually play out? Well, the display function takes our abstract struct day array, which, let's be honest, to the computer is literally just raw blocks of memory, and magically transforms it into a human-readable schedule. It simply loops sequentially through each day, printing the data out nicely inside neat, dashed lines. It's super simple, highly effective, and a great example of how contiguous blocks of memory map perfectly to linear, everyday tasks. Moving right along to part 2, binary search tree operations. Time to step up into hierarchical data. To make the jump from a flat line to a tree, we need a brand new building block. Enter the node. Kind of like our calendar struct, it holds data, in this case, an integer. But the absolute game changer here is the addition of 2 pointers, a left pointer and a right pointer. In C, these are literal memory addresses telling us exactly where the next data blocks live. By just adding these 2 directional addresses, we fundamentally change our data structure. We go from a flat array to a branching hierarchy, where every single node can point to 2 entirely distinct child nodes beneath it. Now, how exactly do we read a branching tree? With linear arrays, it's easy. We just read from index 0 to 6. But with a tree, we have to use depth-first traversals. We've got 3 main flavors here: in order, pre-order, and post-order. Notice how the placement of the root dictates the exact order we process the data. In order, we visit the left branch, then the root, then the right. For pre-order, the root comes first, then left, then right. And post-order saves the root for the very end. It's just a beautifully systematic way to explore nonlinear data using recursive function calls. Okay, quick question for you to ponder. We've got this massive branching tree of data now. How do we actually find a specific value quickly without having to painfully check every single node one by one? In a flat array, worst case scenario, we have to look at everything. And that simply doesn't scale. The answer lies in the sheer elegance of binary search tree logic. Because of how we build it, the tree naturally sorts itself. To find a value, we just compare our key to the root. Is it smaller? Well, it must be down the left branch. Larger? Head to the right. With literally every single step, we eliminate half of the remaining tree. This recursive logic turns what could be a massive search into a lightning-fast operation, shifting our time complexity from a slow linear search to a highly efficient big O of log n. Stepping up to part 3, navigating city graphs. Let's talk about interconnected nodes. Trees are great, but they really only flow in one direction, downward. In reality, it's rarely that simple. Think about a map of cities. Roads go back and forth, connecting multiple towns in this massive, chaotic web. To represent this in C, we use an adjacency matrix. If you want to ground this abstract concept, just picture it as a simple grid map. It's a 2D array where rows and columns represent different cities. If there's a road connecting city A to city B, we pop a 1 in that grid intersection. If not, a 0. Boom. We've logically mapped out a complex graph using a mathematically simple 2D array, which gives us instant, order-of-one lookups in C. Now, the number 20 is actually super important here. In the source code we're analyzing, the adjacency matrix is strictly capped at a 20 by 20 grid. Why set a hard limit like that? Well, it highlights the real-world memory bounds that programmers absolutely have to consider. Unlike our dynamic calendar that asked for exact memory on the fly, this graph uses a fixed 2D array. It's a very deliberate design choice. We are basically trading the flexibility of dynamic allocation for the sheer raw speed and simplicity of contiguous memory blocks in a pre-sized matrix. Which brings us to our final section, Part 4, BFS versus DFS, the ultimate search strategy showdown. Let's break this down methodically, because in computer science, everything is a trade-off. Breadth-first search, or BFS, explores level-wise, kind of like a ripple spreading out in a pond, checking all the immediate neighbors first. Depth-first search, or DFS, goes depth-wise. Imagine a maze runner picking a single path and sprinting as far as possible before hitting a dead end and turning back. Because of these completely distinct approaches, BFS leverages a queue data structure, while DFS uses recursion, which acts entirely as a stack. And honestly, choosing between a queue and a stack totally dictates your search behavior. BFS relies on a queue. Think of waiting in line at a coffee shop. It uses front and rear pointers to ensure that the cities closest to the start are explored first, radiating outwards step by step. DFS, on the flip side, uses recursion. It basically calls itself, plunging deeper and deeper into the graph along a single path until it literally can't go any further. Only then does the stack unwind to backtrack and try a new route. The real-world consequences of these mechanics really show up when we talk about shortest paths and memory usage. BFS is absolutely guaranteed to find the shortest path between two cities, which is a massive advantage. But there's a catch. That superpower demands much higher memory usage because the queue has to actively remember all the cities on the current level. DFS doesn't guarantee the shortest path at all, but its memory footprint is way lower since the call stack is only tracking the current singular path being explored. Well, we've really scaled the complexity ladder today, haven't we? We went from the linear organization of daily schedules to the recursive branching of search trees, all the way to mapping out city grids with complex traversal algorithms. We've seen firsthand how memory constraints, data structures, and pure logic intertwined in C to solve entirely different problems with amazing efficiency. So I'll leave you with this final thought. Balancing the trade-offs of memory versus speed. Which data structure is going to power the core of your next program? Keep learning, keep building, and I will see you in the next explainer.